Let us now look at the different variables of a gas. So there's 4 variables. You have pressure, volume, temperature, and amount of gas, that is number of moles of the gas. Normally, pressure is measured in Pascal. IB will often use kilopascal. Volume is, the SI unit of volume is meter cube. IB will often use dm cube. Temperature, SI unit is Kelvin. IB will use degrees Celsius. And amount of gas, that's usually in moles, but sometimes you're given mass. Then you'll have to convert mass to number of moles. So you'll use the equation, number of moles is mass over mR. Now, conversions are given in section 4 of the data booklet. So you can convert degrees Celsius to Kelvin. So degrees Celsius plus 273.15, you get temperature in Kelvin. You can convert dm cube to meter cube. So if you divide by 1,000, and these conditions are given, we're going to see that a little bit later. And normally, when we're looking at a gas, all these 4 variables will be changing. But for the sake of investigation, we're going to change only 2 of the variables and then we keep the rest constant. For example, we're going to increase pressure and then we see how volume is affected, but we're going to keep temperature and amount of gas constant. We can look at how pressure is affected by temperature. So we can increase temperature and then we see what happens to pressure. But then we're going to keep volume and number of moles constant. So whenever we're investigating a gas, we're going to keep 2 things constant and then we investigate the other 2 variables. Now, one thing that you have to be careful whenever you're using any of these variables, when you're using values from these variables, the temperature must always be in Kelvin. Normally, if pressure is in kilopascal, the volume must be in dm cube. If the pressure is in Pascal, the volume must be in meter cube. IB advises that you keep everything in SI units, which means that temperature in Kelvin, pressure in Pascal, and volume in meter cube. But you're going to see that in certain conditions, you can mix them up, but you have to ensure that pressure is in kilopascal and volume is in dm cube. And if pressure is in Pascal, volume must be in meter cube. So keep this in mind. Now let's look at how we are changing 2 variables and keeping 2 things constant. So we'll start with Avogadro's law, and you don't need to recall all the names of the different laws, but you have to know how to sketch the graphs and how to manipulate them and apply them in calculations. So this is Avogadro's law, which looks at how volume changes with number of moles while keeping temperature and pressure constant. So it was found that volume of a gas is directly proportional to the amount of the gas. So if we were to sketch a graph of volume against number of moles, we would find that it is a straight line like this, right? So because it is directly proportional. So what does that mean? It means that equal volumes of different gases contain the same number of particles. So if you look at this example here you have 2.02 grams, 4 grams, 16.05 grams of different gases, right? But if you look at the number of moles of each of these gases, so each of them, if you find number of moles using mass over mR, so for each of them, you're going to find that they consist of 1 mole of gas, right? So 1 mole of each of these gases, if we look at them, we see that they occupy 22.7 dm cube at standard temperature and pressure. Standard temperature pressure is called STP, and at STP, temperature is 0 degrees Celsius and we are at atmospheric pressure, so 100 kilopascal. These conditions are given in section 4 of the data booklet. So this is the STP conditions. And here you have the SATP conditions. This is standard atmospheric temperature and pressure. So here we are at 25 degrees Celsius and atmospheric pressure 100 kilopascal. So at STP, 1 mole of any gas occupies 22.7 dm cube. So if we know the volume of a gas, we can divide by 22.7 dm cube to get the number of moles of the gas. Right? So volume of a gas divided by molar volume. This is called the molar volume that we are going to abbreviate as Vm. So number of moles of any gas is volume of the gas divided by molar volume. Right? And molar volume, you have to know that at STP, molar volume is 22.7 dm cube. This is found in the data booklet. But at SATP, the molar volume is 24 dm cube. Okay? So if we look at this question, it says each of these balloons occupy 22.7 dm cube. State the conditions at which this statement is true. So molar volume is 22.7, therefore the conditions are 273 Kelvin and 100 kilopascal. And why is this statement true? Because each of these balloons contain 1 mole of gas. So for all of them, 1 mole of gas is present in that volume. Let's see another question. So a 2 dm cube sample has mass of this much. Determine the molar mass. Right? So molar mass is mR. And if you remember, to find mR, we can use the formula number of moles is mass over mR. So to find mR, we need mass and number of moles. Mass is given, number of moles, we need to find it. And we are given the volume of the gas. So we can use number of moles is volume divided by molar volume. And it says that it is at STP. So then molar volume is 22.7 dm cube. So then number of moles will be 2 dm cube divided by 22.7 dm cube. Then from this we can find the mR using mass over number of moles. So 2.47 divided by, I'm going to take my calculator value here because this is my final answer, not this. And I have 28.0 gram per mole. And I'm giving my answer to free SF because this is to free SF and this is to free SF. The next question, you have to determine molar mass in gram per mole of an elemental gaseous substance. This is the density. So density is 3.12 gram per dm cube, which means that 1 dm cube of the gas weighs 3.12 grams. So you need to find the molar mass. Again, we're going to use mR is mass over number of moles. Now mass we are given, this is the mass, right? So this is the mass. Now we need to find the number of moles. So number of moles is volume divided by molar volume. It is at STP, so molar volume is 22.7. And the volume, if you see here, this mass occupies 1 dm cube. So this is the volume. So this is 1 dm cube. Now, 22.7, this is found in the data booklet. You don't need to memorize it. If you look at section 2 of the data booklet, you can see molar volume of an ideal gas, 22.7 dm cube. Okay, so this is what we're using. You find the number of moles, and then you do mass divided by number of moles. Mass is this, number of moles is this, and you have 70.9 gram per mole. Right? Now it says that you need to identify the substance if it is diatomic, which means that this is twice the AR value. So it is diatomic, which means that it is X2, right? So AR value of X will be 70.9 divided by 2. So 35.45. Now you look in the periodic table and you find the element that has AR value of this. This corresponds to chlorine. Therefore, the substance is chlorine Cl2. Last question. You have carbon monoxide reacting with oxygen, and then you need to find the volume of carbon dioxide produced. Now, the first equation that we've seen in relationship to volume and number of moles is volume divided by molar volume. That's the first equation. The second thing that we are going to see here is that because volume and number of moles are directly proportional, whenever you have a chemical equation, you can use volume ratio just as you would use mole ratio because they are directly proportional, right? So, for example, here we have 2 moles of carbon monoxide reacting with 1 mole of oxygen, producing 2 moles of carbon dioxide, right? So the volume ratio, this is the mole ratio. Then the volume ratio, this is 40 centimeter cube, reacting with, so 40 will be reacting with 20 centimeter cube of oxygen because the ratio is 2:1. So even if I am providing 40 centimeter cube of oxygen, this is in excess. So only 20 is reacting because of the mole ratio. And this is going to give 40 centimeter cube of carbon dioxide because this is 2:2. So 40:40. So then volume of carbon dioxide produced is 40 centimeter cube. So there isn't much calculation here because mole ratio can be equated to volume ratio. So make sure you remember these two when working with volume and number of moles.